Welcome to the Winds and Currents webinar. Today we have Larry O'Neill from Oregon State, who's going to talk about feasibility of estimating sea surface height and geostrophic and Ekman currents from a potential Odyssey mission. So I'll let you take it away, Larry.
Yeah, well, thank you, everybody. Happy Tuesday morning. So today I'm going to talk about a project that I started to embarked on a couple years ago with a couple of the co-authors here, Dudley Chelton, Ernesto Rodriguez, Roger Samuelson, and Alex Weinatier. And we wanted to actually just ask the question about whether if we had, an instrument that could measure surface currents spatially, if there's a way somehow that we can estimate properties about the sea surface height field from it. And it wasn't, if what we could learn from that. And one of the kind of exciting prospects of this is that, if it's feasible to do this, you could have something like an Odyssey instrument or whatever ends up coming out of this could end up being something like a wide swath altimeter. Of course, it wouldn't replace conventional altimeters, but it would provide more information than what we have that's kind of contemporaneous in space and time. So this project goal was just to explore whether it's possible and feasible to estimate sea surface height from surface ocean currents. And this was a suggestion that was originally made at a ocean vector wind science team meeting about 5 or 6 years ago. Actually, it seems like a long time ago, by Ross Hoffman in La Jolla. And really this concept of seeing if we could have something like a wide swath altimeter to have sea surface heights that gave you sea surface height that was together with surface currents and surface winds. And so this is basically just an application to test whether Doppler scalerometers can yield accurate sea surface height fields. And then partly with this, and this was kind of something that came out of the work of doing this, is that this method actually gives estimates of the Ekman and geostrophic velocity components and is a potential tool for approaching the separation of balanced and unbalanced flow in the surface currents. So we'll probably see why in a moment here. And so the methodology that we used at the time so I've tried a couple different approaches to this, both statistical and dynamical, and it turned out the dynamical approaches were the best. And I'll show a couple of approaches in a moment. It basically relates the surface currents and winds to sea surface height anomalies using momentum budgets here. And we developed this procedure using a coupled WRF-ROM simulation off the US West Coast. And so I've shown a nice map here of the model domain. And so the California current, so this is the US West Coast, and the California current system is really kind of a nice place to test this because it's really dynamically active. We have lots of eddies, as you see here, and the colors here show the sea surface height anomalies. And then we also have the meandering upwelling front along the coast. And so there are lots of filaments and meanders in the front. So it's really a kind of a dynamically active region and a really good region to test the validity of whatever reconstruction approach that we do. And so the coupled WRF-ROM simulation, so we had hourly output for 43 days, and this was during the summer upwelling season from October and September of 2009. And this approach, what we wanted to do is develop a method that used only the surface currents and the surface wind stresses to try to estimate the sea surface height anomaly. And the application for this was to basically be able to apply this directly to a Doppler scalerometer such as Odyssey here. And I'll say just for a moment that there's no particular reason we needed to use a coupled ocean atmosphere simulation. It's just what we had available on hand at the time. And this simulation does not have tidal forcing or Stokes drift in it. And so this is one area that we need to work on in the future to see if tides and then the Stokes drift will affect the reconstruction approach. And the reason Stokes drift is important here, of course, is that it is a component of what a Doppler scalerometer will see in the surface velocity that it measures here. We don't think it's a big deal, but we don't know for sure. And the boundaries of this model were just forced with global HICOM and ERA interim. And I didn't mention it, or I didn't put it down here, but the model, the ocean model grid spacing was 2 kilometers in both directions. So it's a fairly high resolution simulation here. So the first dynamical approach that we take to the reconstruction, and we refer to this as reconstruction R1. And this basically is the simplest one that you can think of, and it treats the surface currents as geostrofically balanced with the sea-surface height anomalies. And so in this sense, we get the surface current measurements U and V, and then our unknowns here are the spatial gradients in eta or the sea-surface height anomalies. So how do we get the sea-surface height anomalies from the surface currents using this formulation? And what we do is you just simply cross-differentiate to yield a Poisson's equation. And so this is here. So we have a Laplacian of the eta is equal to the curl of this vector F here, which in this case is just the curl of the ocean currents. And this is a relatively straightforward partial differential equation to solve. So you can obtain a unique solution by specifying boundary conditions for the sea-surface height anomalies along the model boundaries and coastlines. So our method here will depend on having some ancillary source of sea-surface height information along the boundaries and things. And I'll talk about that a little bit in a minute. And then you can, the numerical solution for this is Poisson's equation. I just use the standard, what's called a successive over relaxation algorithm or SOAR algorithm. And this will yield a unique solution given the boundary conditions that you're given. And I won't talk too much more about this today, but this method will yield a stream function that's in this case related to the sea-surface height. But it also, with some additional effort, you can also get the velocity potential field. And so this whole reconstruction gives you what's called the Helmholtz-Hodge decomposition of F. And it's kind of a nice way of, this provides a nice way of getting the stream function and velocity potential field given the sea-surface height anomalies on their boundary conditions here. And for development purposes, we have implemented the boundary conditions using the known sea-surface height anomaly from the ROMS model. And what this will kind of give us a best case scenario for noise and bias-free sea-surface height anomaly and currents, given the model doesn't have errors in it. Further down towards the end of my talk, I will talk about the sensitivity to uncertainties in your boundary condition for sea-surface height anomalies. So let's see how this method does. And so this first one, I just showed a snapshot of the reconstructed sea-surface height anomaly, and it's at simulation hour 777. So it's a lucky number. And did we get lucky? So the left-hand map here shows the reconstructed sea-surface height, just using the geostrophic approximation. And the middle map here shows the model's true sea-surface height. And so you see that there's a pretty good correspondence between the two. The reconstruction gets most of these eddies and filaments pretty well. And then when you look at the difference between the two at the snapshot, you can see that actually the reconstruction it has a lot of errors. So the errors here on the order of about plus or minus 12 centimeters. And there's obviously big errors throughout the domain here. So while this approach does get the mesoscale eddy field pretty well, it has large scale biases and stuff that really limit the reconstruction accuracy. So now, I had 1,032 hours of the simulation in which to do this reconstruction on. So I computed basically the error statistics just to verify what it's, how accurate the method is. And this left-hand map here shows the RMS error of the reconstruction. And of course, on the boundaries, since the error goes to 0 because we use the model's true boundary condition. But as we get into the middle domain, it's not as affected. The solution isn't as affected by the boundary conditions. And so that's where we get the big errors here. And the RMS errors here are in the order of about 12 centimeters maximum in this northern part of the domain. And then it gets to about 4 centimeters towards the bottom. And I'll talk about why the spatial structure is the way it is in a moment. There's also fairly substantial bias in the reconstruction. So the biases are in the order of about plus or minus, on the magnitude of about 5 or 6 centimeters. And then the model skill here, the model skill is just defined as the square of the cross correlation coefficient between the reconstructed sea surface height and the true sea surface height anomaly. And very disappointingly, the model has almost no skill throughout a lot of the domain here. So our model using the geostrophic approximation is relatively inaccurate here. So, and we'll delve on why in a moment. But what I'm going to do is I'm going to, for a couple different reconstructions, I'm going to just show some simple error statistics for the whole domain here. And the first one, reconstruction, was using geostrophy here. So if you integrate over the whole domain, model domain, excluding anything near the prescribed boundary conditions, the RMS error using this is about 6.7 centimeters. There's about a 1.3 centimeter bias, and a model skill throughout the domain is about 0.635. So, you know, this it's fairly substantial error, even though the model field or the reconstructed fields, you know, qualitatively capture a lot of the mesoscale structure in the California current system here. So what can we do about this? So our approach here was just to kind of throw more physics at it and see what sticks. So the next reconstruction approach, which we call reconstruction 4 or R4, we apply corrections to the surface currents for Ekman and advective contributions. And essentially, we just followed the momentum balance for the surface ocean currents here, steady state ocean balance, which is a very important point here. So the Ekman current components, our approach here was to use just the simplest slab layer model for the ocean currents. And so it just, you just have a slab of the surface ocean that's some depth, which we call RE, HE. And it's just related to either it's kind of related to the ocean mixed layer depth or the Ekman depth here. And all it assumes is that the top of the slab is driven by the wind stress, and then the bottom is driven by a Rayleigh drag, a simple linear Rayleigh drag here. And when you do that, you can algebraically solve for this steady state Ekman velocities, UE and VE, according to this. And so this method needs the surface wind stress. And fortunately, an instrument like Odyssey will measure the surface wind stress. So that's great. But we also need these this frictional depth and this linear friction coefficient at the base of the frictional layer. And for this study, you know, we tried a couple different ways of doing this, and we essentially used ones that are essentially constant in time and space. And you know, this actually didn't do too badly. So we note also that there are more sophisticated ways of dealing with the Ekman currents, getting an Ekman current solution. And at this stage, we didn't apply this yet because we're still just kind of in the exploratory stage. And to be honest with you, this simple Ekman model actually worked out fairly well, at least for the low frequency component of the Ekman current velocities. The Ekman, the horizontal advective components, this is fairly straightforward. Since we'll have the U and V current fields in the ocean, we can get their spatial derivatives and estimate the advective components here. We'll note that this advective components correction was fairly small and was really mostly significant near really small eddies, nonlinear mesoscale eddies. For the most part, it didn't do very much, but we kept it in here anyway because this is just a free source of information that Odyssey will be able to measure here. So how did this reconstruction do? So here's a snapshot here. And so this was the reconstructed sea surface heights, the true sea surface height, and then the difference between them. And so while throwing these additional physics into it did reduce some of the error in the reconstruction, it didn't really reduce it very far. So now we've got instantaneous errors on the order of about 10 centimeters throughout the domain here. But we still have this big structure here in the northern part where we have a lot of error of various signs here. So, and then if we do it for all 1,032 hours of simulation, the RMS error here is actually reduced quite a bit compared to the geostrophic case. Now we're getting errors that are kind of more towards 8 to 10 centimeters in the northern part of the domain. But one thing that really changed substantially was the bias. The bias was substantially reduced throughout the domain here. So it's closer to zero and, excuse me, doesn't have quite as much spatial structure as it did in the geostrophic case. On the other hand, the model skill, it is actually, it still looks pretty bad, but it is actually improved a bit compared to the geostrophic case here. But we still have a lot of regions here where the skill is, much lower than 0.5. So, this method also still has relatively low reconstruction skill and accuracy here. So when we just do this over the whole model domain, so apply the advective and Ekman corrections here in R4, the RMS error throughout the whole domain is reduced to 5.7 centimeters. And then the bias is, the magnitude of the bias is reduced to about 0.4 centimeters. And the skill actually goes up, fairly decently to 0.736. So even though these additional physics improve the reconstruction, it's still actually relatively inaccurate. So, the question is, can we do better? What is keeping us from being able to accurately reconstruct the sea surface height here? And this is where we start to learn some really cool things. So the first thing I did to kind of get a handle at this is to look at the squared cross-coherence spectrum for the reconstructed sea surface height anomaly and the model's true sea surface height anomaly. And I used reconstruction R4 here, which had the Ekman and advective components here. So this is a cross-coherence spectrum. I did it in frequency space, so that's in the y-axis here, and then zonal wave number space. So I just did it throughout all the latitudes in the domain along constant latitudes here. And so the color scale here, so it's squared coherence. So the values are between 0 and 1. So 0 is no coherence, and 1 is perfect coherence here. And the dark green is what we want to see. And so for a lot of the low frequency components, so frequencies less than the inertial, about 50 hours or so, the reconstruction actually does quite well for all wavelengths here. So that's actually good news that there's, a good part of the spectrum that the reconstruction is good for. What we really start to have problems with is when we get to periods less than 50 hours and when we get towards the inertial period, and that's where the spectrum goes white or gets to near 0 here. So the reconstruction is doing very poorly at resolving inertial variability in the currents. And then I also have signatures of inertia gravity waves here. And so I applied the first dispersion curves of the first 4 vertical modes of internal inertia gravity waves in the coastal ocean. So you could kind of see there's some whiskers here in the cross-coherence spectrum that line up very nicely with the dispersion curves here. So not only in inertial variability, but also inertia gravity waves seem to be causing very poor reconstruction skill in here. So basically from this is that we know that for periods greater than 50 hours, reconstruction actually performs quite well. So we get squared coherences that are greater than about 0.9 throughout the domain here. And it's always nice to see just some raw time series just to show exactly what we're looking at here. And so I just picked a point in the middle of the domain in this magenta box here at 39 degrees north and 128 west. And this is a time series here of the true sea surface height at that point for the model simulation. And the time coordinate here that I'm using is just the number of inertial periods from the start of the simulation. And you'll see why I picked that time coordinate in a second. So this was reconstruction R1 with the geostrophic approximation on top of it. So you can see that, there's obviously very strong inertial variability that's superimposed on top of the model sea surface height variability. So we know, so it becomes very apparent that the inertial variability in the surface currents are contaminating our reconstruction here. The R4 reconstruction with geostrophy and the Ekman and advective corrections applied doesn't do much, does a little better at places, but doesn't do much better. So that's what the green curve here shows. If you look at just the variance in the near inertial band of the surface currents, I've just shown maps where I've taken the rotary spectra of the surface currents and split them into clockwise and counterclockwise variants, and then just integrated within the near inertial band, which is between about 6 and 25 hours. And what you can see here, and this is a log scale. The colors here are the variance, and it's on a kind of a log scale here. And so in the northern part of the domain, we get, so first off is we get a lot more clockwise variability than counterclockwise. So this is a hallmark of inertial motions in the northern hemisphere. And then the clockwise variability was much stronger in the northern part of the domains by a couple order of magnitudes than the southern part of the domain here. And so in a nutshell, this is why the reconstruction performs so poorly up in the northern part of the domain, is that you have these very strong inertial variability that just happens to be present during this time period in the domain here. And we do get some counterclockwise variability, but you know, it's very, very small compared to the clockwise variability here. So we know that we have an inertial current problem in the currents, and this is contaminating our reconstruction pretty badly here. And this is just kind of the same sort of plot, but shown in a different way. And it just shows the ratio of clockwise to counterclockwise velocity variance as a function of frequency and latitude here. And then these open circles just show the inertial frequency at each latitude. So you can see it gets, the inertial frequency decreases as you go towards the equator. And so you see that the ratio of clockwise to counterclockwise variance follows very well this along the inertial band here. So essentially clockwise inertial currents are very energetic on time periods less than about 50 hours in the domain here. And so after experimentation, one way we chose to mitigate this in our reconstruction was just actually apply a simple temporal smoothing of our input F vectors into our reconstruction. So let's see how that does. So we've initially did a 50-hour smoothing with a reconstruction R4. So that's shown in this magenta line in this time series here. And so you show that the agreement between the true sea-surface height field, the red, and the magenta curves are much better. And then obviously we've gotten rid of a lot of the evidence of inertial variability in the currents. And so the reconstruction really gets quite a bit more accurate after applying this temporal smoothing. And then, if a little smoothing is good, a lot must be better, right? So if we do another reconstruction R8 with 150-hour smoothing, and that's shown by this brown curve here. And so we show that we get a little bit better agreement between the model sea-surface height and then the reconstructed sea-surface height here. So temporal smoothing, is a kind of a promising technique to mitigate inertial current variability. And so let's see how this, how the statistics look here. So this is, so we first did the, looked at just the instantaneous fields with the 50-hour temporal smoothing. So we call this one from R6 here. And so this is the, this left-hand panel and map is the reconstructed sea-surface height field. And the middle map here is the true sea-surface height field, and then the difference between them here. So with temporal smoothing, we see all this large-scale differences that we had at this time period are now completely gone. And now we have much smaller magnitudes error throughout the model domain, and it's a little bit more homogeneous spatially here as well. And just to remind you, this were the errors that we had in the reconstruction R4 that did not have those errors here. So we've substantially reduced the errors, reconstruction errors, with temporal smoothing here. So you look at the accuracy assessment. So this was the R4 that I showed earlier. So this was the terrible skill and then the really high RMS error, especially in the northern part of the domain. But now when we do this 50-hour smoothing, the RMS error now is much reduced. So this is all below about 2 centimeters throughout the domain. The bias is unchanged, and the bias is unchanged because the smoothing only removes variability. It doesn't remove any biases in the inertial currents. And then the skill really improves throughout most of the domain. So the skill throughout most of the domain is now well above 0.9, except for maybe for a small patch here in the center of the domain. And I'm not sure exactly why this is here, but it's it's still fairly good throughout most of the model domain. So temporal smoothing really increases their reconstruction accuracy by mitigating near inertial variability in the currents. And we had to use temporal smoothing because we don't have the physics included in our model that can account for inertial current variability here. So, so now I have our table just as an updates now to using this 50-hour smoothing, the reconstruction R6. The domain RMS error now is reduced from 5.7 centimeters to 1.3 centimeters. And the model skill is now increased substantially to 0.984 from 0.736. And then if we look at just 150-hour smoothing, we do get a slight increase in the RMS, decrease in the RMS error and a slight increase in model skill, but it's really, you start to get into diminishing returns when you, apply an increasingly long window in your time smoother. So kind of from this, we've concluded that our ability to accurately estimate the sea surface height anomaly from surface currents and wind stresses is not severely limited by dynamics or ill-posed inverse problems. But this applies at least for the noise-free and well-sampled case and for perfect boundary conditions. So as you can see where this is leading, we're not going to have, if we have an Odyssey instrument and we had a boundary conditions from a gridded sea surface height product like a VISO or something like that, we're going to have measurement errors in the currents and winds, and we're going to have uncertainties in our boundary conditions and sea surface height. So, so it begs the question about how sensitive our reconstruction accuracy is to these sort of things. And so, fortunately, we have a test bed with this model simulation that we could kind of get some insight into this and whether this would actually work for an Odyssey instrument. So the first one is how would random measurement noise in the currents and winds affect our reconstruction accuracy? And so to do this, we added some random noise, Gaussian distributed random noise to both the currents and the wind vectors, and they're uncorrelated between the vector components. And for the surface currents, we added about noise with a standard deviation of 0.354 meters per second, which is the projected baseline error in the Odyssey surface current measurements that are estimated. And then for the wind stress components, we added noise that was 0.04 Newton per meter squared to each wind stress vector component here. And this was also kind of a baseline error estimate from the Odyssey wind measurements when you after you convert it to wind stress. And so this just shows one realization of these random measurement noise at our favorite simulation hour of 777. So you can see it's pretty noisy. They look pretty noisy here. So certainly this must really reduce our reconstruction accuracy. And it does, so when you run this through our reconstruction, using reconstruction R4, which had the Ekman and Invective corrections applied, but this doesn't have time smoothing in it yet. So this is just a snapshot. So this is the sea surface height anomaly that you get from the noise reconstruction you get from the noise-free case. And this is what you get from the noisy case in the middle panel here. And then this is the difference here. So you do get some random noise throughout the domain, and it's something on an order of plus or minus 2 centimeters. And in fact, the mean RMS difference between these two is about 1.2 centimeters here. So it does add a little bit of, so it does degrade the accuracy of the reconstruction a little bit. But when you do go out through the whole domain here, oops, the projected measurement series uncertainties only increase the RMS error from 5.7 centimeters in R4 to 5.8 centimeters, and reduces the model skill just a tiny bit from 0.736 to 0.728. So from this, we conclude that the projected measurement uncertainties are not driving our reconstruction accuracy here at all. And I should point out also that these measurement uncertainties in the winds and currents are fairly pessimistic estimates. So we don't actually, after the mission is launched, we expect that those uncertainties would actually get smaller. So we really don't expect that the reconstruction accuracy is going to be very sensitive to this. And so that's great news. So What is a little bit more challenging here is that if we did actually have an Odyssey mission, is that it's not going to resolve inertial variability in time from just a single Odyssey instrument here. But our reconstruction accuracy is going to be driven in large extent by how we can mitigate inertial variability in the surface currents. So what would the reconstruction accuracy look like if we had twice daily sampling from a single Odyssey instrument using our reconstruction physics and the time smoothing approach here? And just because I don't want to take up too much time, I'll just get right to the punchline. And if we sample our model twice per day, so every 12 hours, which would be something like an Odyssey, a pole orbiting Odyssey satellite would do, and we apply 150-hour smoothing to it, and then using just our physics from with the Ekman correction and vective correction, the RMS error so would go from about 1.1 centimeters to 2 centimeters, so it would roughly double. And our reconstruction skill would only degrade from 0.99 in this 150-hour smoothing case to 0.966. So right now, it seems like the Odyssey sampling errors would not present a significant challenge in accurate reconstruction of the sea surface height anomalies, although this may depend on your location that you do, so that you have an adequate number of temporal samples per day, so that you can get at least a decent idea of what the inertial current variability is. And the last thing I wanted to just do is look at the effect of boundary condition noise on the reconstruction accuracy. And so all the reconstructions so far have used per the model's sea surface height boundary conditions. So that's those are obviously error-free because they came from the model. So how sensitive is it if we have some uncertainty in the boundary condition model here? And so to answer this question, I just kind of came up with a colored noise model using a spectrum of colored noise in both time and space. And so this gives, so when you run this for the 43-day simulation, this gives a noise standard deviation of about 4.4 centimeters. And I've shown just an instantaneous map of one of the noise here at the top left here. And so this color scale goes from about -12 to +12 here. So definitely a lot of noise that we introduce into the model. And this would be meant to mimic maybe uncertainty that we'd expect from a gridded sea surface height product like Aviso or Echo or something like that. And this is probably a rather pessimistic depiction of what those measurement uncertainties would be. And some of the measurement uncertainties includes random measurement errors in the underlying altimeter measurements in the gridded sea surface height product, but also mapping errors that you would get from putting those from from gridding those in time and space as well. So and then here just shows kind of a time longitude plot of what the noise looks like that I added to it. And so this would be kind of qualitatively consistent with the errors that we'd expect from a gridded sea surface height product. What I did was I ran 50 different noise realizations using this, and then did the reconstruction using those 50 different ensembles here. So I've basically 50 different ensembles of 43-day hourly simulations here, or twice daily simulations here. And so this is what the reconstruction accuracy looks like with these noisy boundary conditions. And this is the RMS error. So this is one of the most important parts of this, is the RMS error is quite big on the boundaries, but actually decreases as you go in. And this is with 50-hour smoothing, 50-hour time smoothing as well. So the RMS error goes down to about 2 centimeters within the domain, and then it increases to about 4 centimeters within 50 kilometers of the domain throughout here. And the mean difference, the bias in the reconstruction, is unchanged. And then the skill does degrade somewhat as you go into the model interior, especially where you get some of these eddies here on the westward side of the domain. And just for reference, this was the reconstruction with the clean boundary conditions, or the unnoised boundary conditions here. And so this is kind of what the comparison is, what we were looking to compare here. So the uncertainty in the boundary conditions are a concern for reconstruction accuracy, but more or less within about 50 kilometers of the model domain here. So within that, the accuracy is still pretty good. And I'll just also emphasize too that this level of noise in the boundary conditions is probably rather pessimistic. It's probably going to be more than less than half of this, but we really wanted to whack this reconstruction pretty hard to see how sensitive it was to these, to the boundary condition uncertainties here. So anyway, the results that we have from all this is that it is feasible to obtain relatively accurate sea surface height anomalies from surface currents. And so our ability to do so is not limited by the dynamics of the system, the opposed inverse problems of getting sea surface height from surface currents, or projected measurement noise in an Odyssey type instrument. We will need to mitigate near inertial oscillations and variability, and smoothing in time is but one option. There are probably others that we could do so, but at some point we'll also need to presumably take into account tides, and smoothing in time might be a good candidate solution to take care of both, mitigate both things. So, and while I didn't really talk about it, this method also yields estimate of the Ekman and geostrophic currents and the irrotational and non-divergent current components. And it also yields the velocity, potential, and stream function here. So really, you get a lot of really good information here, and these are all dynamically consistent with the sea surface height and the surface currents. So this is really kind of a really nice set of potential data sources with this instrument. One thing is that the uncertainty in the specified boundary condition degrades the accuracy of the interior sea surface height reconstruction. And so for the Odyssey instruments, if we're looking forward to that, possible sources of boundary conditions are something like a VISO or ECHO interpolated to the swaths, edges, and coastlines. But that would still have to be developed in time. And finally, we can only account for the Ekman component of the wind drift in our model. So right now it's unknown how much the Stokes drift that is naturally measured by the Doppler scatterometer will affect the reconstructed sea surface height anomaly. We suspect it won't have much effect, and that's, but we don't know for sure as well. So future work that we're going to analyze a longer time record of using the Odyssey simulator data, and to look at further look at near inertial oscillations, internal waves, and tidal flow components, and test our ideas of using a VISO and ECHO to grid, to help provide boundary conditions for the gridding approach. So the slab layer approach to the Ekman current correction is actually not great. And what I mean by that is it basically will, it gets kind of the mean low frequency part of the Ekman currents. It doesn't give you the higher frequency parts of the Ekman current flow. So any sort of wind-induced inertial oscillations and things in the currents. We would like to actually move beyond using a slab layer approach into more sophisticated methods, but that's something we are looking to tackle in the future. And then we also want to extend the reconstruction approach to separate balanced and unbalanced motions. So I think we have a lot of the tools here to do that. And we do plan in the future to do this. What I'd like to do is to have a better Ekman model loads to do this here. And then finally, just to assess applications of the velocity potential information. And so I've done some work on this, but preliminary analysis suggests that the large scale vertical velocity potential field is actually very well correlated with near surface vertical velocity in the ocean. And so, in addition to having the sea surface height anomaly, this reconstruction approach might actually gives us some information on the, kind of mesoscale vertical velocity field. So anyway, with that, I'm all done, and I'll take any questions.
And thanks very much, Larry. This was great. Maybe to get started, there are a couple questions in the chat that were sort of clarifying questions, but we could go back. Fabrice asked about your variance. I think the units were labeled meters squared per second squared, and he was wondering if it was actually centimeters squared per second squared.
Yeah, it probably is. Oops, thank you. I heard that there.
And Deirdre Burns said, does the model have atmospheric forcing? I'm just wondering what kind of high frequency noise that might add.
It does have, so it is, it's coupled to a WRF simulation. So it has, the whole spectrum of atmospheric forcing added to it. So, and I guess if it's coupled, it's pretty high frequency atmospheric forcing. Yeah, and like I said, it doesn't strictly, this analysis doesn't depend so much on it being a coupled simulation, but it's just what we kind of had on hand. So Melanie has her hand up.
Oh, hi, Larry. Interesting talk. Thanks. I guess I have a pair of questions that maybe go together. One, I'm sorry, I missed whether you said whether the model has rivers in it. So I'm wondering if you think the reason there's more inertial energy in the northern part of the domain is from the Fraser and Columbia making the slab layer thinner. And then in a related question, for your Ekman slab layer, how did you determine the mixed layer depth? And if you used a variable one from the model, how much effect do you think it would have, using Odyssey data where you don't have mixed layer depth other than from Argo in a lot of places? Yeah, that's a great question. So the answer is that and Roger can correct me if I'm wrong, but it does not have river inputs into it. Okay. And then the second question is, so we actually used for the slab layer model, I just used a time invariant and space invariant slab layer depth and friction coefficient. So it doesn't have any variability from that. So that is kind of a, so I did include at some points, variable slab layer depth and variable friction coefficient, and actually didn't really have any effect on the solution accuracy. So, just for simplicity, I used kind of a spatially, I temporally and spatially averaged values. Okay, yeah. So why do you think there is so much more inertial energy in the northern half of your domain then? It was from essentially there was more atmospheric variability up there. Okay. There's more wind variance. Yeah. From just the storm track position, I guess. Yeah, and I'm not sure that there were kind of some, this was kind of in the summer, so there wasn't really many storms, but there was definitely more wind variability up there. There were a couple weak fronts that came through at this time, and so that kind of kicked off some inertial variability. Thanks. Yeah. I can follow up on that, Larry. You said this was in the summer. Have you thought about, I guess I'm wondering when in the summer and what might the seasonality be? If you had 43 days of winter instead. Oh, yeah. Excuse me. So that's something I actually hope to look at with the Odyssey simulator data, is like a longer time record that can get the whole annual cycle. But this simulation was from August to September. And so it was when the upwelling front was the most active here. But yeah, during the winter time, I think that the inertial current variability would be much greater because the increased variability in the winds, among other things. So yeah, that's a good question. But maybe also a difference in the slab layer thickness. Yeah. So Luna has her hand up. Still muted.
Sorry, yes. I'm a postdoc at FSU. That was a very nice talk. Thank you for that. I was wondering if you calculated the model skill for a case of smoothing only the geostrophic field, because if you smooth 150 hours, then you might get rid of most of the dynamics involved, the Ekman and the advection that you said was mostly around nonlinear eddies. And that would avoid, getting, having to deal with the HE and RE and extra calculations.
Yeah, that's really, so I did many different versions of the reconstruction with different smoothing and different physics and modification stuff, but I did do that. And so I should say that we do have a paper in review right now on this, essentially on most of what this talk was, and it kind of outlines some of the things in more detail. But just to get in your case, so we did that reconstruction, and the RMS error with 50-hour smoothing on just using the geostrophic approximation, the RMS error reduced to about 3.5 centimeters, but there was still a substantial bias in the reconstruction. So it was about minus 1.3 centimeters still. And but the model skill went up to about 0.898. So
okay.
yeah, so it does actually do pretty well. Not as well as so that was actually encouraging. So it's most of the variability, or a lot of the variability in the surface currents, are tied to the sea surface height.
But that means that you're still missing out some physics then if you... Yeah, okay.
Yeah.
Thank you.
Can I ask, while people are thinking of other questions, what the addition of, I think you said the model does not have tides, or no, it did have tides?
No, it
doesn't have tides and internal waves. So I don't know how much it supports internal waves, but have you thought about what those might do? Or would that be like noise, or is that going to be another confusion?
Yeah, it's probably going to be, we're hoping to do that with the Odyssey simulator data. And of course, that data is based on like the MIT GCM, or I believe, which has, there's
exuberant tides.
Yeah, but it's also not clear how well, if it overestimates internal wave or internal
right, yeah,
wave variability, or underestimates it. But it hopefully would give us a little bit better idea of what it is. Hopefully, to be honest with you, for the system, it'd actually be better if it overestimated the internal wave variability, because then we'd get a good idea of what the sensitivity of the reconstruction would be.
Yeah, that makes sense. And then I have to ask about the prospects for applying this to HFR data, to observations.
Yeah, I have thought about it, but I haven't, since I don't work with that data. I'm not sure how well this reconstruction would do. One thing I'm thinking about is that the spatial extent offshore that it goes, it's on the order of, I believe, 100 to 200 kilometers. And that might be kind of on the short end of what this method's, the physics that this method's valid for. But one thing I was going to show was I did do this reconstruction, apply it to some Doppler scat data during S mode. And this actually might get a little bit on what it would look like to apply it to HF radar data. So just so everyone knows, S mode was off the coast of California, and we were in this red polygon here. And there were repeat tracks of Doppler scat. So this just shows a section of Doppler scat data on one particular day. And then this grid here, so what's shown in the colors is sea surface height. This outer grid here is the Aviso sea surface height on this day. And then in here is the reconstruction from the Doppler scat winds and currents here. So this is kind of what it would look like. There is no time smoothing applied here, so this should be really taken for entertainment purposes only, because the currents will have inertial variability, and we actually do know that during S mode, the inertial variability was pretty strong in parts of the domain. But it's actually quite amazing that the Doppler scat currents were actually qualitatively consistent with the large scale sea surface height field. And then the reconstruction did show some, finer resolution, structure to the sea surface height field that's possible. Whether this is accurate or not, we don't know. But this would look like possibly how it would look like as well with like HFR radar data or something.
You have LiDAR data from the same flight period? Did the Luc Linaz instrument go over there at the same time?
Yeah, we do. Yeah, we have LiDAR and then radiosonde wind measurements too. So
wonderful.
Yeah, so it's really unique collection of observations to look at air sea interaction and surface currents and how is it, the whole thing.
Well, are there other questions? If not, I have more questions, but maybe we should be talking offline, Larry, rather than me torturing everybody else with arcane details. This has been really great, and I appreciate you doing this, and it's a really fun results. Thanks a lot, everybody. I'm going to stop recording.